Hi everyone, we are Team 3, consists of Donggili, Jinrujan, and Hunijo. Let me start our final presentation. First, we're gonna revisit our topic with baseline paper. This is a brief introduction for those new to our presentation. And then we explain the limitation of existing method and our improvement approach. Finally, we clearly show our improvement result with evaluation and discussion. We verify that our proposed method is superior than any other SOTA method. Our topic is related to visual SLAM. Visual SLAM means that simultaneously estimate the robot position and create a map around the robot using vision sensor like camera. For this, the robot have to estimate the depth of each pixel using the disparity between left and right camera images like human eyes. For the depth estimation, we use an event camera, which has recently been attracting attention as a sensor for SLAM. It mimics the human eye and, unlike a normal camera, only captures areas where there is a change in pixel brightness. Therefore, it consumes less power, operates very fast, robust motion blur. So, our baseline paper is to estimate depths from stereo event sequences using end-to-end learning, called Learning on Event Sequence Embedding for Dense Event-Based Deep Stereo. For the event depth estimation, they propose an embedding taking into account spatial positions of 2 dimensions plus temporal coordinate of 1 dimension effectively. However, our baseline paper has some limitations. The most important problem is that detailed information is missed, as you can see in the top middle figure. This is because event information is sparse compared to image. Furthermore, the image-only based method is very vulnerable to the motion blur. To solve the problem of our baseline paper, we proposed a method of fusing event and image with complementary characteristics. For that, we developed the attention map for our fusion model. Also, for efficient fusion, we create the multi-scale feature fusion method.
Okay, I will explain about the proposed method. Our proposed overall framework consists of a total of 6 sub-networks. The 6 sub-networks are event embedding network, feature extractor, vision model, multi-scale correlation, 3D aggregation, and sparse disparity branch. The order of each model will be explained in order of the model closest to the input of the model. First of all, I will explain the feature extractor and event embedding network. The feature extractor generates the high-level features from events and image respectively. Both the event feature extractor and the image feature extractor have a resonant structure, and the receptive field is improved through dilation. Each feature extractor generates 3 feature maps of different sizes. Event data stream data are accumulated for a certain period of time in the form of a first in, first out queue and converted into a 3-dimensional image form through continuous MRP. Through this embedding, event data can be used as an image by CNN. Events and images pass through the first 3 convolutions and are extracted as the largest size of one feature map. And as the layer passes, the size of the channel dimension increases and the size of the height and width decreases, which is extracted as a feature map. 3 feature maps of different sizes are generated. Next, I will explain the fusion model. Feature maps of events and images generated at multiple scales are merged through the fusion model. Fusion model extracts only semantic information from images and transfers them to event features. Since the input image features and event features are multiple scales, the output is also a fusion feature map of multiple scales. The fusion model combines events and image features in pairs through the EIF module. Events and image features of the same size enter the same EIF module and become one fused feature. As shown in the figure below, the EIF module is composite of EIA develop and EIA down, which will be explained in detail in the next slide. The EIA develop is composite of 2 branches, event and image path. First, the event features are converted into event codes through convolution, instance node, and relu activation layer. Similarly, image pictures are converted into image codes through layers of the same structure to deliver semantic information as events. And in order to remove the unnecessary pictures while leaving the necessary pictures in the image code, the sigmoid function is used to transform it into a spatial attention map having a value of 0 to 1. Next, the attention map is multiplied by the event code and added first event feature with residual connection, so that the event branch output is delivered to the next EIT block. The image branch concatenates the result from the event branch and delivers them to the next EIT block. EIT down is a method proposed to effectively reduce the channel dimension of the fused feature map, and the overall structure is the same as that of the EIT block, and there is no residual connection, and the channel output of the finally fused feature is reduced by half compared to the input. Next, I will explain the spatial-wise multiscale correlation model. The fused left and right event and image pictures become a cost volume through the correlation model. It receives the multiple scales as input and effectively considers large-scale features through cost-by structure. The cost volume has a four-dimensional size with the Dmax axis added, which is the maximum disparity. The spatial-wise multiscale correlation we propose is by applying a patch proportional to the size of two features of multiple scales. It makes three input features of different size into a one cost volume of the same size. The final cost volume is created by concatenating the three cost volumes. Next, I will explain the 3D aggregation network that extract the disparity map. The generated cost volume must be converted into a probability volume with a probability for each disparity per pixel in order to extract disparity. When the aggregation network is trained, the intermediate network will estimate the disparity, generating four outputs. When testing, only the last output model 3 is used for inference. Finally, I will explain the sparse disparity branch proposed to robustly use the event feature. In order to effectively utilize the characteristic of data called event, we propose a dual learning method through a sparse branch. In sparse disparity is estimated only for the region where the event occurred recently, and the loss is also given only for the region, effectively using the characteristics of the event. These sparse branches are designed to be used only for the learning and not used for testing or inference, effectively handling computational resource. Next, I will explain about the loss. For the loss, smooth loss, which is mainly used in depth estimation, was used. For small values, scale values are used, and for large values, absolute values are used. Loss is given for both sparse and dense, and there are 4 outputs each, so there are a total of 8 disparity 8 outputs.
Then we conducted an experiment. First, let me explain the dataset. For performance evaluation, MVSCC comprised indoor data through a drone was used. 2 Davis event cameras are attached to the drone, and LiDAR is attached for ground truth. In addition, we create synthetic driving dataset to compare with RGB stereo images. The virtual data was created by Blender 3D computer graphics, and event data was created by eSIM. For actual driving scenarios, we also added blur to the image. This is qualitative result. As you can see at D, by using event and image together, a disparity map that effectively distinguishes the shape and edge of an object can create. And disparity is well obtained not only in real data, but also in virtual data. As evaluation metrics, one pixel accuracy, mean disparity error, mean depth error, and median depth error, which are mainly used in stereo matching, were used. When testing, we also measure the time it takes to inference one disparity map. Since all stereo studies using events have compared the performance of event stereos, the stereo results using images are additionally needed. So we trained various models using MVSC. The proposed model SMCNet was trained without a sparse branch and was trained even after adding it. We also compared the recently published paper that uses both images and events in stereo. In all performance evaluations, the proposed model outperformed the other models, and the time required to generate the disparate map did not increase significantly. Also, evaluation was performed on a virtual dataset. Virtual dataset used RGB images rather than intensity imaging, so we also trained several models. Although RGB-based results outperform event-based models, the proposed model outperforms the RGB-based models. For the ablation study on the fusion module, it was compared using CONCAP or the SPADE module used in other transport studies. As a result of performance, the proposed EIAT fusion module showed the best performance except for the mean disparity and median depth error of split 3. An ablation study of the proposed correlation method was conducted. Only the proposed fusion module EIAT was added and was also trained by removing the sparse branch for a fair comparison. The proposed SMCNet shows good performance in all evaluation metrics. In conclusion, we introduced the baseline paper about event-based stereo matching and reproduced the paper's results successfully. Then we proposed advanced network based on the paper, and this is the first approach combining event images with event sequence. For this network, we propose an attention-based fusion module, a spatial-wise multi-scale correlation method, and a novel sparse branch mechanism. All results were compared with existing results, therefore we concluded that we proposed successful network. Thank you for listening.